So continuity is the idea that if I have a point here and I have another point there, that I can connect them by drawing some kind of curve or line from one to the other without lifting my pen. That's the idea of continuity. And if I zoom in there, there's no breaks. So it's a line or curve with no breaks. And either a function is continuous or discontinuous. So functions are either continuous or discontinuous. And most of the functions you've seen in your career are continuous for the most part, but once in a while some weird stuff happens. So examples of continuous are linear functions. And linear functions are a part of a more general class of function called polynomials. Right, so straight lines, we can draw them continuous. Polynomials, you know, that might be like y equals x cubed minus 3x squared plus 3x minus 1 might look something like that. And it drops down that way and it goes up that way. And it has no breaks in it at all. But functions can have breaks in them. They're what are called step functions. And piecewise functions, except I before E, we're just going to go with it. Piecewise functions. So a step function might be a function that starts at a point and then goes horizontal for a little bit and then stops, and then it picks up here, maybe at that same x value, but a different y, and then it steps out a little bit, and then we pick up here, and then we keep going, and maybe it just goes that way forever. Right, so this has breaks in it. Sometimes functions have holes in them, so there's a lot of ways to be discontinuous. I could have a hole, I could have an asymptote. I could spell asymptote with an S, please. And the way we define continuous is in terms of limits. So 3 conditions have to be met for a function to be continuous at a point. And then if we look at a whole bunch of points, we can say it's continuous over its domain. So continuity rules. So the first rule about continuity is that if we plug in some value, then we get an answer. Let's call it L. If we plug in and there's no answer, it's undefined, then we're done. There's nothing to do. Okay, so if we know that has a value there, then 2, what we want to check is, does it have a limit? So we want that to exist. And the third thing is we want these 2 things to be equal. We want the limit as x approaches a of the function to actually be the function value at a. All right, so if those guys match up, we're good. You can kind of summarize it into this third step right here, but this doesn't necessarily apply. The limit exists, but those are the 3 rules right there. So if we have those things happen, if there's a function value and the function behaves nice on each side, right? This is a 2-sided limit here. And a 2-sided limit means on the left it looks good and on the right it looks good. So limit as x approaches a on the left side has to equal the limit as x approaches a on the right side. And both of those have to be actually equal to the function value that we hope exists. Right? And we've kind of played with polynomials. And if you just think about the idea of here's a point and a function passes through that point, right? If I can draw it like that, if a computer can draw it like that, then it looks like the limit is approaching on the left and on the right, and we have the point there, a f of a. So we have a good left-sided limit, we have a good right-sided limit, and the point exists, we're cool, we're continuous. If any one of these fails, then the function's discontinuous. Now, as far as continuity goes and discontinuity, there is a special type of discontinuity that we're going to look at called the point discontinuity, or a removable discontinuity. And we get a removable discontinuity when this part right here is true, right? Which is essentially rules 2 and 3, but rule 1 is not true. So removable discontinuity, rule 1 fails, but rules 2 and 3 are good. Right, we can plug the hole. And we've seen examples of that. So in the previous section, we had a homework problem. This one right here, if we look at this function, f of x equals square root of x minus 6 over x minus 36, it looks nice and smooth, but at the point where x equals 36, it had no y value. Y did not exist. But the limit did exist, so I can plug that hole with the limit. So if I look back at the graph of this function, here, I can plug the hole in this function with the point 3612. Otherwise, that didn't exist. So if I just get rid of that point for a minute and I go to look here where these guys intersect, I'm going to find that there's going to be a hole right at 36. Right? There's no value of that green function there. But I know that I can make that point because of the limit 36 comma 1/12, and I can fill the hole. That's called a removable discontinuity. So I could redefine this function as a new function that is continuous, and I would do it as follows. So to plug a hole, we have to make a piecewise function. And let's go here. So for example, f of x is equal to x square root of x minus 6 over x minus 36. Now, because of the square root on the top here, the domain of this function is x is greater than 0, or greater than or equal to 0 is actually okay there. And because of the denominator here, x cannot be 36. So if I put that in interval notation, the domain goes from 0 all the way up to 36. And then I have to stop right before 36, union, pick up at 36, and then keep going to the right forever. Right? So this designates that there's that hole there. Right? F of 36 is undefined. So I'm going to create a new function, g of x, and I'm going to make g of x in pieces. So piecewise function, we put a curly bracket, and I'm going to put the first piece as 1/12, and it's 1/12 if x equals 36. And then otherwise, I use the formula x minus 6. Oops, that's a weird 6. Over x, square root of x minus 6 over x minus 36 if x is greater than 0 and x is not 36. Right, so I'm plugging that hole right there with this new function g of x. And this function right here is continuous for x greater than or equal to 0. Next thing. If we just look at, say, f of x equals the square root of x on a graph and think about when it's continuous, so f of x equals the square root of x. The idea of continuous involves a two-sided limit, which means I need to look at the left and the right. We have a problem here at the origin where this function basically starts, because I can take a limit on the right side, but there is no left side to take a limit of. So we also have the idea of left continuous and right continuous, which just is the left-sided limit and the right-sided limit. So back to my notes. So this function here is continuous for x greater than 0. The domain of this sucker, however, is x is greater than or equal to 0, but I can't say it's continuous at 0 because continuous implies it's continuous on the left and the right, has a limit on the left and the right, and there's nothing going on to the left here. So it's what we call right continuous. At x equals 0, because I can only take the limit as x approaches 0 on the right side of the square root of x because of the domain, because I'm working with real numbers here. And that limit is 0 in this case. Lots of zeros floating around there. So you can have a function that is left continuous, right continuous, and you can have some weirder cases. What about y, or let's use function notation. Let's say r of x equals 1 over x. What do we know about this function right here? Well, I know x can't be 0, so the domain of this thing right here would be x. Let's use, we can use inequality notation. X is greater than 0, or x is less than 0. And interval notation, try that again. Domain could be written as from 0 to the left forever, union 0 to the right forever. And I have to use parentheses, not square brackets, because I can't use 0 and infinity is not a number. It always gets a parenthesis there. So as far as continuity here, this function is continuous over its domain. And its domain is any number that's greater than 0, any number that's less than 0. You pick in one of those numbers and we can show that the limit on the left exists, the limit on the right exists, right? For example, at x equals 0.0001, tenths, hundred thousandths, 10 thousandths, right? That's 1/10,000th. And if I plug that into my function, and ask my calculator what that is, the calculator says, well, just flip x. So x, the y value would be 10,000. Right? My calculator would say that right there. And if I explore the limit on a calculator as x approaches 0.0001 of 1 over x, I'm going to find that it is also 10,000. It behaves nice on each side. And however close to 0 I get, positive or negative, it's going to be nice like that. What about at 0? Easy answer is x equals 0 is not in the domain, so who cares? But there's a reason I'm bringing this up. Besides that, let's look at the limit as x approaches 0 on the right side of 1 over x. So that means I have to pick numbers that are positive but close to 0. And what that means is I'm plugging in small numbers. So small positive numbers. And if you plug a small positive number into a denominator, right, it gets flipped to be a large positive number. Large positive numbers, as x gets smaller, the reciprocal gets bigger. And so basically this means it increases forever. And if I look on the other side, if I try to take the limit as x approaches 0 on the left side, that means I'm plugging in small negative numbers into 1 over x. And if you take the reciprocal of a negative number, you get a positive number that's far from 0. So basically you're decreasing forever, getting away from 0 on the other side. And does this exist? And remember, this is just a fancy way of saying does not exist. Right? I'm saying the limit does not exist, but it increases forever. Here I'm saying the limit does not exist, but it decreases forever. And sometimes we'll also say without bound. Right? There's no boundary you can make that this thing can't surpass heading down, is what's going on there. So remember, infinity and negative infinity are just special ways of saying doesn't exist with a little bit of extra information. Otherwise, this function is continuous for any number but 0.